Gas mixtures. This chapter introduces the fundamental concept of gas mixtures in engineering thermodynamics and explains why it is important for energy system analysis. Gas mixtures appear in many real applications, such as air, exhaust gases, and fuel mixtures. The main focus is how mixture properties can be derived from the properties of individual components. The discussion links these ideas to the ideal gas law and real gas deviations. This framework forms the basis for analyzing pressure, volume, and temperature in multi-component systems.
The gas mixtures topic is positioned after power cycles, refrigeration cycles, and thermodynamic property relations. This sequence indicates that students already have a foundation in energy, work, and pure substance properties. With that foundation, the analysis is extended to systems containing more than one component. This reflects real conditions in energy and process industries. The chapter serves as a bridge toward gas-vapor mixtures and chemical reactions.
Learning outcomes. The learning outcomes emphasize the ability to determine mixture properties from composition and component properties. Students are expected to define mass fraction, mole fraction, and volume fraction correctly. The rules for ideal gas and real gas mixtures are also introduced. Predicting PVT behavior using Dalton's and Amigat's laws becomes a key competence. The final goal is a systematic and quantitative analysis of gas mixtures.
Total mass in non-reacting mixtures. The total mass of a non-reacting gas mixture is simply the sum of the masses of each component. There is no mass change because no chemical reaction occurs. The example of 6 kilograms of hydrogen and 32 kilograms of oxygen giving 38 kilograms illustrates this additive principle. This concept is essential for mass balance in both closed and open systems. This simple rule becomes the basis for further mixture calculations. Total moles in non-reacting mixtures. The total number of moles in a mixture is also additive, just like mass. If there are 3 kilomoles of H2 and 1 kilomole of O2, the total becomes 4 kilomoles. This concept is consistent with the definition of amount of substance in chemistry and thermodynamics. A molar basis is very useful because many equations of state are written in molar form. This naturally leads to the concept of mole fraction. Mole fractions in gas mixtures. Mole fraction represents the proportion of each component relative to the total moles of the mixture. The sum of all mole fractions is always equal to 1, reflecting a normalized composition. The example of an H2 and O2 mixture with 0.75 and 0.25 shows this quantitatively. This concept is crucial because many mixture properties are expressed as mole fraction weighted averages. Mole fraction also plays a direct role in Dalton's and Amigat's laws. In a gas mixture, the sum of the mole fractions of all components is always equal to 1. Dalton's law of additive pressures. Dalton's law states that the total pressure of an ideal gas mixture is the sum of the partial pressures of each component. Each gas is assumed to occupy the same volume at the same temperature as the mixture. Mathematically, for gases A and B, P mix equals PA plus PB. This concept allows the separation of each component's contribution to the total pressure. The approach is widely used in air and exhaust gas analysis. Amigat's law of additive volumes is the sum of the volumes of each component at the same pressure and temperature. Each component is imagined to occupy a portion of the total volume. Mathematically, for two gases, V mix equals VA plus VB. This law is the volumetric analogy of Dalton's law. It helps in understanding the concept of component volumes in mixtures. Component volumes and total volume. Component volume is defined as the volume a gas would occupy if it were alone at the mixture pressure and temperature.
The example shows O2 occupying 0.3 meters cubed and N2 occupying 0.7 meters cubed under the same conditions. Their sum gives a total mixture volume of 1 meter cubed. This provides a clear visualization of how Amigat's law works. The concept reinforces the idea that mixture volume can be viewed as the sum of individual contributions.
Compressibility factor, Z, for real gas mixtures. The compressibility factor Z is used to describe the deviation of a real gas mixture from ideal gas behavior. The mixture equation of state is written as Pm Vm equals Zm Nm Ru Tm to include non-ideal effects. The value of Zm is not arbitrary, but is calculated as a weighted sum of the compressibility factors of the components. The weights are the mole fractions of each component in the mixture. In this way, the PVT behavior of real gas mixtures can be estimated more realistically.
Answer C. By summing the weighted compressibility factors of individual gases based on their mole fractions. Explanation of why other answers are wrong. A. By dividing the total pressure of the mixture by the total volume. Incorrect, because this does not account for the mole fraction or the individual gas behavior needed to calculate Zm. B. By taking the average of the individual gas compressibility factors without weighting. Incorrect, because Zm requires weighting by the mole fraction of each component, not a simple average. D. By using the ideal gas law directly for the mixture without considering individual gas behavior. Incorrect, because Zm specifically adjusts for deviations from ideal gas behavior, which the ideal gas law does not account for.
Pseudo-pure substance approach. The pseudo-pure approach treats a gas mixture as a single substance with averaged properties. The critical properties of the mixture, such as critical pressure and critical temperature, are calculated as weighted sums of the components' critical properties. With these pseudo-critical properties, real gas charts and correlations can be used as if the mixture were a pure substance. This approach simplifies calculations for complex mixtures. Its accuracy is sufficient for many engineering applications.
Extensive properties of a mixture. Extensive properties such as internal energy, mass, and volume are additive in a mixture. The total value of a mixture property is simply the sum of the contributions from each component. The example shows that the total internal energy, Um, is obtained from UA plus UB. This principle is consistent with the definition of extensive properties that depend on system size. This concept is essential for energy balance calculations in mixture systems.
Weighted averaging of intensive properties. Intensive properties, such as specific energy or specific volume, are not directly additive. For mixtures, these properties are calculated as weighted averages based on the amount or fraction of each component. The example shows the calculation of an average value of 560 kilojoules per kilomole from two components. This method ensures that each component's contribution is accounted for proportionally. This approach is widely used in ideal gas mixture analysis.
Entropy changes in ideal gas mixtures. Entropy changes in ideal gas mixtures are analyzed based on the partial pressures of each component, not the total pressure. Each component has its own entropy change that depends on the initial and final states. The formula involves the natural logarithm of the ratio of partial pressures. This shows that mixing and state changes affect each component individually. This approach is important for analyzing mixing and separation processes.
Real gas mixtures and molecular interactions. In real gas mixtures, interactions between different molecules lead to more complex behavior. Pressure and volume no longer follow simple additive rules, as in ideal gases. Dissimilar molecules influence each other, causing deviations that are not easy to predict with simple models. This makes the calculation of real gas mixture properties more challenging. Therefore, special approaches such as compressibility factors or the pseudo-pure method are required. In real gas mixtures, molecular interactions between dissimilar molecules lead to unpredictable changes in pressure and volume. References and closing. This chapter is mainly based on the textbook by Chengal, Bowles, and Kanolu, which is a standard reference in engineering thermodynamics. All figures and concepts follow the theoretical framework of that reference. This ensures consistency between the lectures and the main textbook. With this foundation, gas mixture analysis can be applied to many engineering applications. This chapter also serves as a basis for gas-vapor mixtures and chemical reaction topics.